Good day, students. In this clip, we're going to be going over how to derive the quotient formula for complex numbers in polar form. So let's go ahead and write down the instructions as to what we're going to prove. So what we're going to do is we're going to show that um, if we have two complex numbers, z1 and z2, so if z1, the first complex number, equals r1 uh, cosine theta 1 plus I sine theta 1, and uh, z2, the second complex number, with the index of 2, equals r sub 2 cosine theta 2 plus I sine theta 2. If we have these two complex numbers, I want to show that if this is the case, then their quotient z1 over z2 can be given by the formula r1 over r2 times cosine theta 1 minus theta 2 plus I sine theta 1 minus theta 2. Okay? So this is a quotient formula for complex numbers. When you're dividing complex numbers in polar form, you just take the quotient of the radii and you take the cosine of the difference of the angles and I sine the difference of the angles. Alright, so this is what we're going to be showing. Alright, there are two identities we're going to be using in this derivation. So let's go ahead and review those real quick. So prerequisite knowledge that's required to execute this proof. The two identities are the difference identities for sine and cosine. Okay, so if you recall, sine alpha minus beta equals sine alpha cosine beta uh, minus cosine alpha sine beta. Okay, this is the difference identity for sine, and then cosine alpha minus beta equals cosine alpha cosine beta plus sine alpha sine beta. Okay. All right. So these are the difference identities for sine and cosine. Now, why am I just focusing on these two identities? If you look at the final result, our target expression, you notice we have the difference identities for sine and cosine. Okay. So that's why we're going to be making use of this two trig identities in completing the derivation. Okay. All right. Let's go ahead and get started. So we're going to start with the left side of our equation, z1 over z2. All right, so what is z1? z1 is r sub 1 cosine theta 1 plus I sine theta 1. And that whole expression divided by um, r2 cosine theta 2 plus I sine theta 2. Okay? All right, now what I want to do is I want to get rid of this cosine and sine on the bottom. So what I'll do is I'll multiply by the conjugate of this denominator, the complex conjugate, okay? So the complex conjugate is what you get when you take the opposite of the sine in the center. So it's going to become cosine theta 2 minus, okay, it was a plus here, we change that plus to a minus, minus I sine theta 2, multiply the top and the bottom by that expression. So in the bottom I'll have cosine theta 2 minus I sine theta 2. Okay, so that's the complex conjugate of the denominator. So what I'm going to do is I'm going to distribute the numerator and the denominator, just follow them out, and then we're going to simplify. Hopefully we can get this result, okay? So let's go ahead and do that. All right, so we're going to write r1 over r2, r1 over r2. Now we're going to distribute the top. When we do the first, we're going to go first, outer, inner, last. When we do the first, we're going to have cosine theta 1, cosine theta 2. First, and when we do the outer, this times that one is going to become minus I cosine theta 1, sine theta 2. Now we're going to do the inner. That's going to be plus I sine theta 1 cosine theta 2. And then the last, plus times a minus is minus I times I square sine theta 1 sine theta 2. Okay? So that's what you get when you distribute the numerator. Alright? So in the denominator, you can clearly see that that's a difference of squares. So if you want to use the difference of squares formula, it's simply cosine squared theta minus uh, I squared sine squared theta. Okay? I can use that shortcut. But let me just show you all the baby steps. Okay? So I'm going to FOIL this out. First, outer inner last. Let's go ahead and do that. First, I'll have cosine. And do that. I'm going to have cosine squared theta 2 for the first. Cosine squared theta 2. And then for the outer, minus I cosine theta 2 sine theta 2. And then for the inner, plus I. Let me use the commutative property of multiplication. I can switch the order of multiplication. So I'll have I cosine theta 2 sine theta 2. And then for the last, I'll have minus, because plus times minus is minus, I square sine square theta 2. Okay? All right. Now let's, you notice this R1 over R2, we leave it alone because it's similar to our desired results. The R1 and R2 already have that, so let's leave it alone. So now, let's see what we can do in the numerator here. This I square, remember, I square equals negative 1, right? I square is negative 1. So now it's going to change its sign to a plus, and I can move this to the front, to the first term. So I'm going to have cosine theta 1, cosine theta 2, plus sine theta 1, sine theta 2. Okay? And here I'm going to reorder these two middle terms and write it as plus, and then factor out the I. Factor out the I, I'm going to have I sine theta 1 cosine theta 2 minus cosine theta 1 sine theta 2. Okay? Alright, that whole expression is the numerator divided by. Now let's see what happens in the denominator. You notice that the middle terms are opposites, right? This and this, they're opposite, so they add up to 0. And then we're going to combine this. We have cosine squared theta, theta 2. I square is negative 1, like we mentioned earlier, so that changes the negative to a plus cosine, plus sine, sine squared theta 2. Okay, sine squared theta 2. Okay? Alright. Now, let's see what happened in the numerator. In the numerator, we're going to have, we notice we have the difference identities for cosine, cosine, sine with a plus. We made mention of that earlier. Cosine, sine with a plus. Oh yeah, I forgot to state another identity that I will use, which is a sine squared theta plus cosine squared theta equals 1. This is the Pythagorean identity, a basic Pythagorean identity. Okay, we're going to use that too. Forgot to state it. Sorry about that. Anyway, this is some difference identities for cosine, as we just saw. So we're going to have R1 over R2. So we have cosine theta 1 minus theta 2. Sine theta 1 minus theta 2. And then over here, this is the the difference identities for sine plus I sine theta 1 minus theta 2. Okay? All right, and then in the denominator, we have sum of cosine square and sine square, and using the Pythagorean identity, that is just 1. Okay, so the denominator becomes 1. Okay, all right, so let's finish it up. We'll just write it nicely as z1 over z2. z1 over z2 is r1 over r2. And we'll just bring this down times cosine theta 1 minus theta 2 plus I sine theta 1 minus theta 2. Okay, so that basically completes our derivation of the quotient formula for complex numbers in polar form. This is the desired result. All right, so that's that. So thanks so much for taking the time to watch this video. Please feel free to subscribe to my channel by clicking up here. And if you like this video, you can click like. And please post a comment to let me know what you think about this presentation. More clips can be found on math.serve.com. Thanks again, and have a wonderful day.